Imagine taking a warehouse full of the world's most extensive supercomputers, setting the entire building on fire, and then, like, launching it out of a cannon at 17,000 miles per hour. That is
basically what's happening.
Yeah, that is essentially what the world's biggest technology companies are actively trying to do right now.
It is the absolute definition of an engineering fever dream. I mean, we are looking at a scenario where the physical infrastructure of the internet is being pushed to such an extreme limit down here on Earth that orbit actually seems like the most logical next step.
Which is wild. And we have an incredibly dense stack of sources today to help us make sense of this. We're looking at a transcribed audio briefing from industry insiders, a highly detailed companion document specifically focused on modular data centers, and a deep dive briefing on the energy economics of artificial intelligence.
Yeah, it's a lot of material.
It is. Okay, let's unpack this, because our mission for today's deep dive is to figure out if blasting server racks into the freezing radioactive vacuum of space is actually, a viable economic escape hatch for the tech industry. Or if this is just an elaborate marketing spin built on fuzzy launch cost maths.
That's right.
And right off the bat, I think we need to draw a hard line around what we are actually talking about here. We are not talking about rocket launch companies, and we're not talking about communications networks like Starlink.
No, those are completely distinct business models. They have totally different bottlenecks.
Yeah.
The focus of the source material today is exclusively on orbital compute.
Okay.
This is about physically locating the heavy matrix math of artificial intelligence up in space and literally selling GPU hours from low Earth orbit.
Right, but to understand why these massive tech giants are even looking to the stars in the first place, we kind of have to look down at the dirt first. The sources keep referring to something called the terrestrial power wall. And, going into this, I assumed, like I think most people do, that AI just uses so much energy that the electricity bill is getting entirely too high.
Sure, that's the common assumption.
But I was reading the energy economics briefing, and the numbers completely contradict that.
Yeah.
Like, electricity only makes up about 7% of the total cost of ownership for a major AI data center.
Yeah.
The chips themselves, the GPUs, are like 60% of the bill. So I have a major pushback here. Why on earth would any rational company spend hundreds of millions, maybe billions of dollars on rocket fuel and aerospace engineering just to save money on the 7% electricity bill?
That is a great question, and that perceived contradiction really highlights a massive misunderstanding in how the public views the AI bottleneck right now. The crisis the tech industry is facing, it isn't the price of the energy.
Okay.
It's the availability of it.
Oh, I see.
Down here on Earth, the physical gigawatts of power that they need to train the next generation of, frontier models literally might not exist to be bought at any price.
So they just can't get the juice,
Yeah.
even with a blank check.
Exactly. The tech industry is slamming headfirst into physical reality. I mean, to build a gigawatt-scale facility today, you have to survive a multi-year municipality permitting queue.
Oh, that's right. Local government.
Yeah, and then you have to physically interconnect to an aging, fragile power grid that was, frankly, never designed for this kind of hyper-concentrated power draw. On top of that, these companies face intense local opposition.
NIMBYism, basically.
Oh, massive NIMBYism. Nobody wants a humming, windowless warehouse the size of a regional shopping mall that guzzles millions of gallons of municipal cooling water.
Built right next to their subdivision.
Right. So the pitch for space is really about skipping the line.
Okay, so how does going to space actually fix that? I mean, obviously there are no zoning boards in orbit, but...
Well, the specific proposal detailed in the briefings involves placing these data centers into a dawn-dusk, sun-synchronous orbit.
Okay, what does that mean?
Essentially, the satellite rides the twilight line between day and night, meaning the Earth never blocks the sun. You get 24/7 sunlight.
Wow.
No night, no clouds, no atmospheric absorption. You just point your solar panels and collect continuous power.
Which gives you the famous free solar energy that all these startup pitch decks are constantly talking about.
Yes.
But the sources actually point out that this is kind of a massive sleight of hand, right?
Oh, completely.
Because the real value to these companies isn't that the solar power is free. The value is that in low Earth orbit, like we said, there's no zoning board.
Exactly.
You don't have to wait 5 years for a local city council to approve a new electrical substation. You are trading aerospace capital expenditure for speed and basically unrestricted access to power.
That's the trade-off, yeah.
But reading through this, there seems to be a fatal flaw in that 24/7 sunlight pitch. If the sun never sets, your servers never get a break from the heat.
Right.
And in a vacuum, that's an engineering nightmare. Wait, actually, let me back up. I'm a little confused here. When we think of space, we think of astronauts in heavy suits to keep from freezing, right?
Sure.
If there's no air in space, shouldn't it be incredibly cold? Why are we worried about heat?
Yeah, that is probably the most counterintuitive part of orbital physics. Temperature is just a measure of how fast atoms are moving, right? On
Uh-huh.
Earth, we use convection to cool things down.
Right.
Heat naturally rises, air molecules carry that heat away, and we use, chilled water and giant industrial fans to speed that process up in a data center. But in the vacuum of space, there is no air.
Right, nothing to carry it away.
Exactly. There are no molecules to carry the heat away from the server. So because of that lack of convection, the vacuum actually acts like a giant thermos. It is a phenomenal insulator.
Oh, wow. So the immense heat generated by these massive racks of GPUs, it just sits there. It has nowhere to go.
Nowhere.
It just pulls in the silicon, basically baking the chips from the inside out.
Exactly. To solve this, aerospace engineers have to rely entirely on thermal radiation. They have to use specialized radiators to physically reject the heat out into deep space as infrared light.
And the scale of these radiators, looking at the companion document, it's just comical.
It really is.
The sources note that to cool just one single megawatt of AI compute in a vacuum, you need a radiator with a surface area of roughly 1,200 square meters.
Yeah.
That is the size of 3 professional basketball courts for 1 megawatt.
Right.
And the newest terrestrial data centers they're building down here are drawing, what, 1,000 megawatt?
Yeah, a gigawatt. It gets structurally terrifying when you realize you can't just unfurl that massive sail and forget about it.
What do you mean?
You have to constantly maneuver that highly reflective structure so it points away from the sun.
Oh, because you don't want it absorbing more heat?
Exactly. But you also have to point it away from the Earth because the Earth reflects massive amounts of heat back up into orbit too.
That sounds impossible. You're flying 3 basketball courts at 17,000 miles per hour, constantly twisting it on multiple axes to avoid the sun and the Earth's reflection,
Yep.
all while trying to maintain, I assume, a laser-precise data link with the ground.
It's incredibly complex, and even if you pull that off, you're flying these delicate microchips through a shooting gallery of radiation.
Right, because down here, our thick atmosphere and the Earth's magnetic field, they protect all our consumer electronics.
Yeah, we take it for granted, but in low Earth orbit, you are exposed to coronal mass ejections.
Solar flares.
Right, solar flares. And high-energy stray cosmic rays.
The briefing mentions this causes something called a bit flip. How exactly does a cosmic ray ruin an AI model? Like, what does that actually look like?
Well, a highly energized particle can pass straight through the physical silicon of a microchip and alter a microscopic memory state. It physically flips a single digit from a 0 to a 1. And AI training relies on adjusting millions of delicate numerical weights across a massive neural network. If a cosmic ray flips a critical gradient during a really heavy calculation, that error compounds as it moves through the network.
So it corrupts the whole thing.
Basically, the AI can start hallucinating garbage outputs, or an entire multi-million-dollar training run can mathematically collapse.
Huh.
You're talking about months of compute ruined by a single stray proton.
Which actually brings up a really interesting technical myth that the source material completely debunks. I read this and it honestly blew my mind.
The ARM processor thing.
Yes. There's this pervasive idea online that to survive in space, you have to use lower power ARM-based processors, like the ones in your smartphone, instead of traditional power-hungry x86 desktop chips.
Mm.
And the myth goes that using ARM somehow slows down artificial intelligence capabilities.
Yeah, it's totally false. The architecture of the host CPU, whether it's ARM or x86, has virtually no impact on the speed of the actual artificial intelligence calculation.
Okay, why is that?
Because in a modern data center, the host CPU is just a traffic cop. Its only job is to organize massive blocks of data and hand them off over PCIe lanes to the accelerator, which is the GPU or the tensor processing unit.
Right.
The GPU is the custom calculator doing the heavy matrix math.
So the traffic cop doesn't determine how fast the cars can physically drive.
Exactly. Aerospace engineers building these orbital platforms, they do not care about brand loyalty or terrestrial chip architecture debates.
They just care about physics.
Right. Their only binding constraints are watts and kilograms. They will use whatever host CPU offers the best energy efficiency to direct that traffic. If an ARMM design uses lower power, which leaves more of the solar budget for the actual GPU, they use ARM.
That makes perfect sense.
Right.
So, okay, let's assume they conquer the brutal thermodynamics. They size the radiators perfectly, they handle the radiation with hardened chips or software redundancy, whatever, and they optimize the watts per kilogram.
Okay.
They still face a bottleneck that moves faster than a solar flare, which is obsolescence.
Oh.
GPU hardware generations turn over every 2 to 3 years right now.
The lifespan trap is arguably the biggest economic hurdle here. I mean, traditional satellites are custom-built, monolithic structures designed to last 5 to 15 years.
Yeah.
If you launch a massive monolithic data center today, it is hopelessly obsolete before its physical lifespan is even half over.
It's like buying a top-tier, incredibly expensive gaming PC, but the case is welded shut.
Yes.
It's glued to your ceiling, and you have to demolish your entire house when the graphics card gets old. It's a wildly expensive, completely brittle business model.
It is. But what's fascinating here is how the industry is actively pivoting to solve this. They recognize what the sources call the non-modular satellite mistake from the early days of telecommunications.
Okay, so what's the fix?
Instead of launching giant all-in-one space stations, the current viable designs rely on swarms of small, highly modular satellites.
Yeah, the sources outline nodes ranging from a few kilowatts up to maybe 200 kilowatts, right?
Right. So you launch a standardized satellite bus. The bus contains all the incredibly expensive, long-lasting components: the structural frame, the solar arrays, the propulsion system, and those massive radiators we talked about.
Right.
But the compute payload itself, the actual GPU tray, is hot swappable.
Oh. So they're essentially server blades just floating in a vacuum.
Literally just swapping them out at 17,000 miles an hour.
That is insane.
And the sources outline major players who are already moving on this architecture. You have StarCloud, which successfully flew a 60-kilogram node containing a flagship NVIDIA H100 chip.
Wow.
You have SpaceX developing the AI-1, which is explicitly designed as an interchangeable chip payload. Blue Origin has filed for Project Sunrise with the FCC, mapping out a constellation of over 51,600 compute satellites.
51,600 satellites. The scale of that is just dizzying. And this isn't just an American endeavor either.
Yeah, not at all.
The briefings highlight that China already has 12 operational satellites in their three-body constellation. And they are actively running Alibaba's Qwen model, which is a heavy-duty large language model, in orbit right now. This isn't just some PowerPoint presentation. Hardware is flying right now.
It is. And the ultimate vision for this modular architecture is that a robotic servicing craft, or like a reusable orbital tug, will eventually rendezvous with the satellite, physically click out the outdated compute tray, and slot in a new generation GPU.
And then what happens to the old one?
You deorbit and burn up the old silicon, but you leave the expensive infrastructure, the power, and the radiators in orbit.
Okay, here's where it gets really interesting to me, though. Even with swappable hardware floating 500 kilometers above us,
Right.
how does a user on Earth actually interact with it? Like, if I pull out my phone right now and ask my AI assistant a question, does my prompt have to beam up to space, get processed by a satellite, and beam back down?
It does, and that introduces the latency deal breaker. The physical distance the light has to travel up to the satellite, plus the processing time to bounce the signal between different satellites using intersatellite laser links, plus the trip back down. It adds roughly 25 to 80 milliseconds of latency.
Which, I mean, that sounds incredibly fast to a human. I probably wouldn't notice an 80 millisecond delay when loading a web page.
You wouldn't, but for a computer operating in the physical world, it's an eternity.
Really?
Think about it. If you are riding in an autonomous vehicle, the car's onboard computer cannot wait an extra 80 milliseconds for a signal from orbit to decide if it should hit the brakes for a pedestrian.
Oh, absolutely not. So does this mean orbital compute is not going to replace our ground-level cell towers?
Ground-based terrestrial infrastructure will always win when it comes to density, penetrating indoor spaces, and millisecond local access. Orbital compute won't replace 5G networks in Manhattan.
Okay, so how do they make it work?
Because of that physical speed of light limitation, AI has to adopt what the sources call a split-brain architecture.
Okay, split brain. Walk me through the mechanics of that.
So the heavy multi-month batch training of frontier AI models, that happens up in the orbital mesh.
Go ahead.
If you are feeding petabytes of text and video data into a model over a 3-month continuous training run, an 80-millisecond delay on the data packets simply doesn't matter.
Because it's not reacting in real time.
Exactly. You use the free, unregulated solar power up there to do the heavy lifting of teaching the model.
But the chatty conversational stuff stays here on Earth.
Right. Real-time inference, the everyday queries we run on our phones, the image generation, the self-driving car logic that stays strictly on the ground running on local edge servers or on the device itself.
Okay, that makes sense.
Yeah.
But training in orbit creates this crazy logistical geometry problem, doesn't it?
Yeah,
These satellites are moving so fast they disappear behind the curvature of the Earth every 90 minutes.
they do.
A ground station only sees a specific satellite for maybe 5 to 7 minutes at a time. So how do you feed a continuous, uninterrupted stream of training data into a server that's constantly playing peekaboo with your antenna?
Well, you can't rely on a single satellite. That's why you need a geographically smeared constellation.
Mirrored constellation.
Yeah, it has to be continuous, unbroken chain of satellites ratting entirely around the planet. They use optical laser links to pass the training data, the neural network weights, the gradients, the active calculations from one node to the next in real time, almost like a relay race.
Wow.
The entire constellation operates as a single, unified, distributed brain.
So the ground station in Texas, say, is just constantly handing off the data stream to whichever satellite happens to be passing overhead in that 5-minute window. And those satellites share the workload amongst themselves using lasers in a vacuum.
Exactly.
That is phenomenal engineering. But it brings us to a harsh reality check, I think. We have to look at what this actually costs the consumer and the massive environmental risk it creates.
Yeah, because free solar power absolutely does not mean cheap AI for the end user.
Exactly. If I'm paying for a monthly ChatGPT subscription, the token economics still apply.
Huh.
The actual cost to generate a word or an image doesn't magically vanish just because the server is floating in space.
No, somebody has to pay for it.
Right. The consumer is still amortizing the massive capital expenditure of the rocket launches, the rapid hardware depreciation we talked about, the sprawling network of ground stations, and the specialized radiation-hardened components. You, the subscriber, are paying for all of it.
And beyond the financial sticker shock, there is a looming environmental cost that the industry is really struggling to answer. What happens when tens of thousands of these modular satellites reach the end of their lifespan and simply die in orbit?
I mean, if a multi-ton orbital GPU farm loses power and fails to actively deorbit itself, it's not just an inconvenience for the company. It becomes a massive piece of space junk flying blindly at 17,000 miles per hour.
Right. And this introduces the very real risk of Kessler syndrome.
Yes, I was reading about this.
This is a scenario where low Earth orbit becomes so incredibly crowded that one single collision, say a dead satellite hitting a discarded rocket booster, creates a massive cloud of shrapnel.
And it doesn't just stop there.
No, at orbital velocities, a tiny screw hitting a radiator shatters it into 1,000 more bullets. That shrapnel then hits other satellites, creating more debris, triggering this unstoppable chain reaction.
It could effectively lock humanity out of space for generations.
Yes.
We would be physically trapped on Earth by a shell of our own broken servers.
It's a dark thought. Deorbiting dead GPU farms is a critical policy crisis that simply hasn't been solved. The industry is proposing putting tens of thousands of new objects into orbit, and ensuring they all safely burn up in the atmosphere upon retirement is a monumental challenge that relies on systems functioning perfectly at the end of their life.
Which they often don't. So what does this all mean? If orbital compute is wildly expensive to launch, plagued by latency that forces this complex split-brain architecture, and threatens to trigger a catastrophic debris cascade that traps us on the planet, why are these tech giants pursuing it so aggressively right now?
Well, if we connect this to the bigger picture, it all comes down to leverage.
Leverage over who?
The mere threat of moving infrastructure off-planet fundamentally alters negotiations with terrestrial local governments.
Oh, wow. It's the ultimate corporate bargaining chip. They are turning local real estate battles into aerospace threats.
Precisely. Think about it. If a major tech giant can walk into a city council meeting and say, if you don't approve the zoning permits and the grid interconnection for our new gigawatt campus by Friday, we will simply pay SpaceX to launch the compute payload into orbit.
That completely upends the power dynamic of terrestrial energy policy.
It does.
And as they push those boundaries, they are opening up a geopolitical and legal minefield. The sources touch on data sovereignty, and it is an unprecedented gray area.
Oh, it's a nightmare for lawyers.
Right. And to be clear to our listeners, we were just neutrally looking at the legal mechanics here from the briefings. We aren't taking a stance on international law.
Mm.
But consider the compliance scenario the sources present.
Right.
You have a data file sitting on a satellite that is legally registered to a U.S. corporation based in Delaware. But right now, that satellite is flying in orbit directly over European airspace. And it is actively training an AI model using consumer data that was collected in Asia.
Whose privacy laws apply in that exact second.
Right. Does the European Union's GDPR apply because the satellite is above their soil? Or does U.S. law apply because of the registration?
Exactly. Traditional data centers are bound by the physical borders of the country they sit in. When you decouple the data from physical borders and put it in constant motion at orbital speeds, the jurisdiction becomes incredibly blurred.
But even with all that freedom in the sky, these companies are still firmly tethered to Earth's geopolitics, aren't they?
Absolutely. You cannot launch your way out of the physical supply chain. The highly advanced TSMC fabrication plants in Taiwan, the complex packaging facilities, you can't print a cutting-edge chip in zero gravity.
Oh.
The silicon has to be manufactured on Earth, which means it's subject to terrestrial bottlenecks.
And you can't launch your way out of ITAR either. The sources specifically highlight export controls.
Yes, the International Traffic in Arms Regulations. The U.S. government treats the most advanced computing technology essentially the same as weapon systems because frontier AI is dual use.
Right, it can write poetry, but it can also design bioweapons.
Right. So to prevent that compute power from falling into the hands of geopolitical rivals, there are strict export controls. Moving a server to space, where theoretically anyone with an antenna could try to interface with it, deeply concerns national security regulators. The atmosphere doesn't void those export controls.
Okay, we have covered a staggering amount of ground and sky today.
We really have.
We started with the terrestrial power wall, where the tech industry is desperately trying to escape multi-year permitting queues and grid bottlenecks by chasing unregulated sunlight.
Yeah, and we climbed up through the brutal thermodynamics of the vacuum thermos, detailing how engineers maneuver radiators the size of 3 basketball courts to bleed off heat while dodging the sun.
We explored the modular revolution, where companies are planning smeared constellations of satellites with robotically hot swappable GPU trays to beat the rapid decay of chip lifespans. We broke down the split-brain architecture required to handle the 80-millisecond latency, keeping training in orbit and inference on the ground.
And we touched on the very real mechanical threats of a Kessler syndrome shrapnel cloud and the unprecedented legal gray areas of data sovereignty and ITAR regulations.
But before we sign off, there was one final provocative thought I want to leave you with, building exactly on those concepts of modularity and jurisdictional gray areas. We talked about how robotic servicing crafts will eventually be able to just fly up and click out a compute tray to upgrade the hardware.
Right, leaving the power bus intact while replacing the silicon.
But if these orbital nodes use standardized, hot swappable connectors, and they contain fully trained, multi-billion-dollar frontier AI models floating in a legal no man's land outside of any single nation's borders, could we see literal space heists?
I mean,
what is to stop an adversary from sending up their own robotic servicing craft to quietly undock and steal a competitor's highly prized GPU tray right out of their satellite?
that is a chilling implication of standardizing hardware in a physical domain with almost zero security enforcement.
I mean, it sounds like sci-fi, but the hardware is standardized. We are looking at a future that is incredibly hard to predict, where the most valuable assets on Earth aren't on Earth anymore. So keep that thought in mind the next time you look up at the night sky.